All right, hello and welcome back to your Chem 4 lecture. We are diving into chapter 3 today on matter and energy. So we're going to start off by talking about matter, what it is. Probably heard that word before. We talked about it briefly in chapter 1. Now we're going to explain it in a little more depth and how we can classify matter. And then what does chemistry have to do with matter? And we'll wrap up by talking about how does matter relate to energy, two separate things that are basically the things that determine uh, what kind of chemistry is going to happen. So yeah, so that's what we're going to focus on this chapter. So first up, let's make sure that we understand the definition of what matter is. It's anything that has mass and occupies space. So this is virtually everything that we interact with on a day-to-day basis. So liquids like water, you have solids like a wooden table, for example, a plastic bag. The air that you breathe has mass and it occupies space, so it's made up of matter as well. And in order for us to kind of talk about matter, we're going to have a few different ways of classifying it. We classify matter according to how it's what it's made up of. Pure substances is one classification, and that's when they have a fixed or definite chemical composition. In other words, in a pure substance, all the particles of that substance have the same chemical identity. And we'll break that down further in the next slide. And then we have mixtures, which is exactly what it sounds like. It's where you have two or more pure substances that are mixed together. And then we talk about whether they mix in one phase or multiple phases, but we'll get to that in a little bit. Okay, so there we go. So this is our classification scheme. As I mentioned already, matter, that's anything that has mass and occupies space, so everything we interact with on a daily basis. And we have two subcategories there, which is pure substances and mixtures. We're going to break down both of those categories into two further on the next few slides here. So let's go ahead. Next up, diving into pure substances. Remember, this is a type of matter that has a fixed composition, and we have two subcategories here. One is the element, and the other is the compound. So an element that hopefully recalls to you the periodic table of the elements. So the periodic table that you see on your tests that we have up in the lab, that shows you all the different types of elements that exist in the universe. And there's 118 that we know of that we've found so far. And this element, basically what it is a pure substance is an element when all the atoms in that substance are that atom of that element. So like the easy example is an aluminum can. Aluminum is an element. You can check it out on the periodic table. Okay, go find it on the periodic table. And sure enough, you see it there. Aluminum, abbreviation AL. And an aluminum can is made up entirely of aluminum atoms. So you see here we have a pure substance because it's all the same type of atom or all the same type of particle. And then it's an element because all of the particles are the same atom. Now that differs from a chemical compound. And a compound basically can be a combination of two or more elements that are always combined in the same proportion. So, so just to kind of back up what we're talking about with elements, all the words or the names that you see on the periodic table, those are examples of elements. So copper, aluminum, lead, carbon, these are all examples of substances that can be found as elements. Compounds, on the other hand, though, you have two or more elements that are chemically combined. So for example, water is an easy example. So you know the formula for water, even if you haven't taken a chemistry class before, you've heard water is H2O. What that means is, every particle of water, what we call a molecule of water, is composed of two atoms of hydrogen and one atom of oxygen. And of course, we're going to spend a lot of time talking about that this semester, but this is kind of your first introduction to this language. Just want to make sure you understand that. Hydrogen peroxide is another example of a compound, H2O2. So that's where you have two oxygens that are combined chemically, and then one hydrogen stuck on each of those oxygens. Very important to note, H2O, H2O2, very different, even though they have very similar ratios. Of course, you can drink water. I strongly recommend staying hydrated with water. If you drink hydrogen peroxide, you will die though. So kind of an idea here that um, you'll see here frequently throughout the class, even just a small change in the chemical formula of a compound. That's what we call this, the chemical formula, can lead to drastically different properties. So sodium chloride, NaCl, that's table salt. You probably have heard of that before. We're composed of 1 atom of sodium for every 1 atom of chlorine that you have. Hydrogen peroxide, of course, 2 atoms of hydrogen for every 2 atoms of oxygen. And there's larger molecules as well, like sugar, which is made of carbohydrates that we'll talk about in a future chapter. And each molecule of sugar, sucrose, is made up of 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. Once we get into the organic and biochemistry section of the class, we'll see a lot of bigger molecules like this. Okay, now interestingly, table salt, sodium chloride, is actually made up of 2 elements that in their elemental form, sodium and chlorine, would be extremely toxic to you. So like chlorine gas, for example, was one of the first chemical weapons that was used in warfare. Sodium metal, if you were to try to eat it, would burn your mouth out. Now, you don't have to worry about that with table salt. It's been combined and an electron has been transferred from an atom of sodium to an atom of chlorine. And you get this nice ionic structure here that has very different properties, of course, because as you know, salt's not gonna hurt you. Okay, so those are our pure substances. Let me know if you have any questions in the comments below. Hopefully that kind of made sense. I know there's a lot. There's a lot of these, so we'll see this kind of over and over again this semester. Okay, next up, mixtures. Now, this should be pretty familiar to you. Just a mixture is any type of matter that has 2 or more substances that are physically mixed, but not chemically combined. You can, for an example here, like if you have spaghetti, you're boiling pasta, right? The pasta water has a bunch of different components in it. Not only do you have the water, you have the pasta noodles themselves, what they're made out of, then any of the starch that dissolves in the water, that's also another part of the mixture. So you see that, it's made up of more things. Now, most substances that we encounter on a daily basis are going to be mixtures. Just for the reason that, and we'll talk about this in the future again, matter tends to mix. It's hard to keep pure substances pure. So unless you have specifically distilled water, okay, that is a pure substance, that's a compound, H2O. Most other things that you encounter on a daily basis are mixtures. In fact, tap water is a mixture. If you look at the components of tap water, not only is it water, H2O, there's also a lot of electrolytes in there. Electrolytes are ions, basically, like sodium, potassium, chloride, all of those that are dissolved in the water. So that's a mixture of 2 or more substances. Okay, so hopefully that kind of makes sense. Now, what we're going to talk about in the lab is we're going to be able to show you how you can separate mixtures. So we have, for example, filtration. This is something that we're going to do a few times this semester. The very basic idea here is that if you take a piece of filter paper and you have a mixture of a solid and a liquid, if you pour the solid liquid mixture into the filter paper, the solid will be captured by the filter, and then the liquid will pass through into the container here. We'll go over these terms in lab, but I'll just say them now that you know that. Of course, the filter paper solid gets caught there. The liquid that passes through the filter is what we call the filtrate. So that's down here. Okay, another thing that can be used is what's called chromatography. And this may be used in a laboratory setting, not just chemistry laboratory. It is sometimes used in clinical laboratories as well. So you may see chromatography, in your future career. So what this is showing you here is that based on capillary effect. So, okay, so think about it this way. If you put a piece of paper, like, let's say you take a paper towel and you stick one corner in a puddle that's on your table. Just spill a little bit of water. Don't try to get your laptop wet or anything like that. But you stick it in there. The water travels up the paper towel, right? That's what we call the capillary effect. You may have heard of. Not super important to this discussion, but the idea is you can stick a piece of paper that has like a dot of a substance, of a mixture on it, and based on how much that substance and the substances in that mixture, like water, they're going to travel up the paper at different rates with the water. So this is what's called chromatography. There's a lot of different, like I say, lab or clinical applications for chromatography, and we'll explore it more in lab as well later this semester. Yeah, not super important. I don't know why I went so in depth there, but it's just good. Hopefully you hear the words and it kind of starts to make sense. Okay, so then, as we said, we have two different categories of mixtures as well. We have homogeneous mixtures and heterogeneous mixtures. So the way that I like to think about this is think of the Latin terms for homogeneous and heterogeneous. So geneous means like phase or mix. So so think of it in terms of like phases. Okay, so homogeneous would translate to same phase. So homogeneous mixtures are ones that just have a single phase. And this is why we say the composition is uniform throughout the sample, and you can't see a difference between them. So these are things like salt water, for example. Like if you dissolve salt in water, you can't see the salt anymore. It's fully dissolved. That's a homogeneous mixture because you can't see a separation. Similarly, things like vodka. Vodka is a mixture of ethanol and water, and it's homogeneous. They occupy the same phase, so they're mixed freely together. And the component, think of it this way: the vodka at the top of the bottle is the same as the vodka at the bottom of the bottle. And here's another example of a homogeneous mixture, which is brass. Brass is a mixture of copper and zinc metal. And if you were to look, with your microscope, your magical microscope, to see the atomic view, you can see that, the composition of the brass is going to be the same no matter where you're looking at on this, I'm going to say tuba. It's not a tuba, French horn, something like that. Okay, so, yeah, so scuba diving, if you're familiar with scuba diving, you may know that when they take these tanks down to breathe your underwater, these tanks are not fully oxygen. They're also not fully air. Air contains nitrogen and oxygen. And then if you're doing like a certain level of diving, you can use the nitrogen and oxygen mixture, not really a problem. But if you're doing a further dive below, you can use what's instead called a mixture of helium and oxygen, which is called heliox. I'm not a scuba diver. I'm not completely familiar with all of these terms, but I do know that, let's see if it's on this next one. Basically, the idea is with scuba diving, you may have heard that when you scuba dive, you need to come up slowly and slowly adjust to the pressure as you come back up from whatever depths you were looking at. And the reason that you have to do that is because if you go up too fast, at great depths, the pressure of the gas is really high, and it's going to dissolve more in your blood. So if you were to just go straight from the ocean floor to the top of the ocean, well, all of a sudden the pressure is lower and the gases aren't as soluble. The gases start to bubble out in your blood, and it's a really terrible symptom, or I don't know what you'd call it, a disease or something called the bends. And I just know that having helium instead of nitrogen is better for that. Is all I know. So you can look that up if you're interested in scuba, and don't get the bends. Okay, so that's a homogeneous mixture. Now, so the reason we talk about this is air obviously is a homogeneous mixture, right? We know air is a mixture of mostly nitrogen and oxygen. Of course, there's carbon dioxide, argon, that stuff, but those are small components of it. And clearly, air is homogeneous, right? It all looks the same. You can't see any separation between the oxygen and the nitrogen. So homogeneous mixture. Now, that brings up heterogeneous mixtures. So different geneous phases. Heterogeneous means there's two or more phases. And in a heterogeneous mixture, the composition is going to vary from one part of the mixture to another. So you'd have something as simple as like put pennies in your water. Well, okay, it's a mixture. You have water, and you have pennies, but the components are clearly separated, right? And you can see easily that there's two different components of this mixture. Okay, so now we're ready for sample exercise number 1. Go ahead, check out the PDF down below that I posted. Print that out or have it ready for you. And we're going to go ahead and classify each of the following as element, compound, homogeneous mixture, or heterogeneous mixture. So go ahead, pause the video, and when we come back, we will have the answers. We'll go through them. See you in a minute. Okay, and we're back. So let's go ahead and classify each of these according to the scheme that we were just talking about. So we have element, compound, homogeneous mixture, heterogeneous mixture. Starting with A, wine. What do you think? Oh, there we go. Wine is a homogeneous mixture. It's, you can see through it. It's like, you can see through a white wine anyway, right? So there's all of the components are dissolved in the water. So it's a homogeneous mixture. Gold, that's an element, right? So you can look on the periodic table. You see gold, that's the element Au. We'll talk more about that in the future. But that's on the periodic table, element. Carbon dioxide has a chemical formula CO2. That's a pretty good piece of evidence that it is a compound. In other words, combination of 2 or more elements. In this case, carbon and oxygen. And then finally, orange juice with pulp, very important. That is a heterogeneous mixture. You have the solid pulp that's mixed in with the liquid orange juice. So again, heterogeneous mixture. Okay, so next up, what we're going to talk about is we're going to talk about the different states of matter. We have solid, liquid, and gas that you've been familiar with for a long time. Now, some of these things are not going to be a surprise to you. Like, for example, we're going to say solids are materials that have a definite shape and a definite volume. No big surprise, right? Well, now we're going to explain to you that the properties of a solid, a liquid, and a gas are actually due to the way that their particles are structured. So, for example, the reason that solids have a definite shape and a definite volume is that the particles that are involved in a solid, so the little atoms or molecules that are there, are stuck in place. They cannot move relative to one another. They can only kind of vibrate a little bit. So they're arranged in those fixed patterns. That means when you take your solid and you dump it out, for example, well, those particles have to stick together. No matter what, they're stuck. So, so that's why, like, a solid has a definite shape and a definite volume. It's not going to expand. They're not going to move away from one another. Those particles are stuck together. And you kind of repeat that throughout to get what we see on the macroscopic scale. Liquids, on the other hand, now liquids have particles that are close together as well, but these particles are moving relative to one another. So like when you look at a glass of water, that water is made up of these water molecules. And these, again, water molecules are made up of 1 atom of oxygen, 2 atoms of hydrogen, looks like this. They're close together, but they're sliding around. They're constantly moving relative to one another. And that's why when you go to pour a liquid, well, the liquid molecules are going to conform to whatever container they're in, because gravity is going to pull them towards the center of the earth. So you pour, and it pours out of the cup. The molecules are just sliding right by one another, and they're getting to the lowest place. They're basically running downhill, getting the area of lowest potential gravity. Gravity's pulling them towards the center of the earth. So liquids always have this definite volume, but they always take the shape of their container. They don't have their own definite shape. And so that's why a liquid will pour like that. And the particles are all moving randomly in different directions. So yeah, so that's what a liquid is there, and that's why a liquid is the way it is. Now, gases, on the other hand, what are some of the properties of gases that you? Well, they have an indefinite shape, right? I mean, for example, you can blow gases from your lungs into a balloon, and whether it's in your lungs or in the balloon, it takes whatever shape it has of its container. The other thing about gases is gases can be compressed, and they can be so they can be compressed into a smaller volume, or you can release the pressure and put them into a bigger volume as well. So they're going to take the shape and the volume of their container. That's kind of the thing about gases. The other thing we know about gases is, for most part, we can see through gases, right? Like you can see through air. Whereas like you look at water and you can see water, you can see through water, but your vision isn't as clear on the other side. And the reason for that basically is that the particles in a gas are very far apart. So before we had solids that are locked next to each other, then we had liquids that were close together and moving relative to one another. And now we have gases where the particles are very far apart. They're moving very quickly in random directions. And they basically don't interact with one another. They're kind of like little ping pong balls, just sort of bouncing off the sides of the walls or bouncing off of each other every so often. We have a full chapter on gases that we'll get to, and the gas laws. They're interesting for their own right, their own respect, but yeah, this just gives you an idea of why these states of matter act the way that they do. Excuse me. So here we go. So solid, liquids, and gases have these different properties. And again, what I want to kind of really draw your attention to here is the arrangement of particles and interaction of particles. For solids, the particles are fixed and they're very close together. For a liquid, they're randomly moving around and they're close together. And then for a gas, they're random and they're very far apart. The interactions between the particles, for a solid, they have to be very strong. For a liquid, less strong. So, just strong is what we say there, but still very significant. And then for gases, there's basically no interactions between these particles. Okay, quick learning check here. Go ahead, identify the state of matter for each of the following, A, B, C, D, and E. Now, this is not on your sample exercise sheet. We're just going to kind of do it together here very quickly. So go ahead, give it a shot. We'll come back and we'll talk about it in just a second. So a vitamin tablet, just like a little pill, that is clearly going to be a solid. Eye drops, they're liquid. Vegetable oil as well is a liquid. Again, it takes the shape of its container. It has a definite volume. A candle, a wax candle, is clearly a solid. It has a definite shape, no matter what container it's in. And then finally, the air in a basketball, well, air is gas. So that gives you an idea here of the state of matter for each of the following. Okay, so now that we've covered states of matter, we've covered the classification of matter, we want to talk about physical properties and chemical properties. This is a way that we can sort of define our conversation about a certain substance. So physical properties are characteristics that are observed or measured, where you can measure or observe them without changing the identity of a substance. So these are things like the shape, the physical state, the boiling point or the freezing point, because remember, the identity of a substance isn't going to change when it boils, right? Water is still water, whether it's ice, liquid water, or water vapor. It's still just that H2O. Density and the color of whatever substance, those are all examples of physical properties, as well as measuring the temperature would be, for example, anything that you can observe, basically. So, okay, so let's give some examples of physical properties by looking at copper. So hopefully we've seen like copper pans before. We can think of like a fresh penny as a copper outside. So to describe copper, you would say, okay, the color is reddish orange. That's a physical property. It's shiny, right? It's shiny like a metal. That's a physical property. You can also measure its conductivity for heat and electricity. And sure enough, it conducts heat and electricity very well. In both of these cases, you're simply heating it up, for example, or passing electricity through it. You're not changing the identity of the copper. You're just kind of measuring different properties of it. At 25 degrees Celsius, it's a solid. So that's about room temperature. It's a solid. The melting point is 1083 degrees Celsius. That's where it goes from solid copper to liquid copper, very high. And then beyond that, the boiling point is 2567 degrees Celsius, just an unimaginable temperature, basically. Okay, so these physical properties can also help us describe physical changes. So a physical change is when matter undergoes a change like a change of state, for example, but the composition is going to stay the same. So we already mentioned this for water. So water can melt from ice to liquid water. Well, okay, so your state is different, right? You went from a solid to a liquid, but the composition of the chemical did not change. It's still H2O. So this is an example of a physical change. And then finally, water can boil into steam. Again, the molecules haven't changed. We still have these molecules of H2O, whether it's in a liquid phase or a gaseous phase. So the composition is the same. This is an example of a physical change. So keep in mind that like the appearance of a substance can also change with a physical change. So salt can be dissolved in water, for example. And you know that you can see solid salt. It looks like this white crystalline substance. You dissolve it in water, and then all of a sudden it's clear. So you might think, oh, well, okay, they went away. It might be a difference, a totally different type of change. But that is still just a physical change. You can recover the salt by boiling off the water, for example, or letting the water evaporate. And then you'll have the same salt crystals that you had before. This is a key part of physical changes. Basically, physical changes can always be reversed, or I shouldn't say always. Physical changes are in terms of changes of state, can be reversed. Now, there's another type of physical change, and the reason that I was so cagey there is a type of physical change would be like taking a piece of paper and ripping. You still have paper, right? And you just have it in two pieces instead of one. Now, that's not exactly reversible. I guess you could tape it together, but I didn't want to get too far into that. But ripping paper, changing state, cutting wood, for example, cutting firewood, those are physical changes. Now, we say all of this to kind of distinguish physical changes from chemical changes. So we need to first define chemical properties. Basically, chemical properties describe the chemical reactivity of a certain substance. That's the ability of a substance to interact with other substances or to change into new substances on its own. And it's difficult to define these chemical properties without defining chemical changes. When a chemical change takes place, you have an original substance that's turned into one or more new substances, which we call products, and that new substance is going to have different physical and chemical properties. So, okay, during a chemical change, you're going to form a new substance, what we call the product, and that new substance is going to have a different composition from what you started off with. It's going to have different physical properties, and it's going to have different chemical properties. So like, for example, look at this like pudding here, okay? So this pudding, you can use like a blowtorch, for example, and what that does is it caramelizes the sugar on the outside of the pudding. And as you know, the pudding is going to taste different from the caramelized sugar on top. That's the carameliness, like it's kind of a famous type of chemical change that occurs in cooking. Another example would be iron nails rusting in water. So iron, is an element, right? It's on the periodic table. It's Fe. You can find it right now. In the presence of water, it can flake off and become like a reddish orange powder. Iron itself is like a nice shiny, metallic color. Rust, however, is like a flaky, powdery substance that's like red or orange in nature that can just flake off. So that's another example of a chemical change. We have this pure substance, iron. It rusts into its rust, which is called iron oxide. Okay, so let's go through this list of examples, and then we'll have like a little quiz here for the sample exercise next. So physical changes include like changes of state, such as water boiling to form water vapor. You can draw copper into thin copper wires. That's another example. You're just changing the shape of the copper. Sugar will dissolve in water to form a solution. You can recover that sugar just by evaporating the water. And then you can cut paper into tiny pieces as well. Okay, so that's all examples of physical changes. We haven't changed the identity of the substance. Chemical changes, on the other hand, change the chemical identity of the substance. So a shiny silver metal might react in air to give a black grainy coating. So like silver tarnishes, for example. That's a metal in the presence of air forming an oxide or a sulfide compound. And so you start with your pure metal, you end with a compound of the metal that has a different chemical and physical properties. A piece of wood burns with a bright flame and produces heat, ashes, carbon dioxide, and water vapor. So it's like your beach bonfire. You do a beach bonfire, start with firewood, well, that wood burns away, right? And you get all of these products, ashes, carbon dioxide, and water vapor. Chemical change. You started with wood molecules, and you ended up with molecules, carbon dioxide, water vapor, whatever is in the ashes. Okay, sugar caramelizing, we talked about this. You form a smooth caramel colored substance that's caramel, and it's got a different chemical composition. It's been oxidized, it's been changed. And sugar tastes different from caramelized sugar. And then finally, iron rusting, right? Iron starts out nice and gray and shiny, and it ends up being orange-red rust. Those are different physical properties because they have different substances. Okay, so yeah, so here's the table just summarizing that. Of course, you can use this in your notes as well. Okay, so here's sample exercise number 2. Let's give it a shot. In the process of attempting to characterize a substance, the chemist makes the following observations, which are physical properties and which are chemical properties. So we're going to go through it step by step. What I want you to do, pause the video, go through A to G, give us the answers, and when you come back, we will take a look at each of them. So go ahead, take a moment. Okay, so A, the substance is a silvery white, lustrous metal. Well, that describes the color, right? So that's a physical property. It melts at 649 degrees Celsius and boils at 1105 degrees Celsius. Well, this is describing the changes of state, right? From solid to liquid and then liquid to gas. These are also physical properties. The density at 20 degrees Celsius is 1.738 grams per centimeter cubed. Density is something that you can measure just with the mass and the volume, which are things that you can measure without changing the identity of the substance. That's also a physical property. Okay, D, the substance burns in air, producing an intense white light. Okay, all right, so that's good to know. And it produces an intense light, and it burns. Well, okay, that suggests that there is a chemical change going on. That is because it is a chemical property. This word burns is a chemical change word. If you see burn, you should think chemical property. Letter E, it reacts with chlorine gas to give a brittle white solid. Again, reacts tells you there's a chemical change. That's a chemical property. F, it can be pounded into thin sheets or drawn into wires. Well, that's just changing the shape. So that's a physical property. And it is a good conductor of electricity. Well, that is also a physical property because you can measure the conductivity without changing the identity of the substance. Okay, sample exercise 3, here we go. Are the following physical or chemical changes? And so go through A through E, give it a shot, and we're gonna pause the video here. And when we come back, we'll go through each of them to know whether they're physical or chemical changes. So go ahead, pause. And we're back. So A, we have the rusting of iron. We talked about this a lot already. Hopefully you figured it out. Rusting, you take a metal and you turn it into its oxide. That's a chemical change. Sugar dissolving in water. Dissolving, well, that doesn't change the identity of the sugar. That means it's just going to be a physical change. Burning a log, we talked about this as well. You take a log and you burn it into carbon dioxide and water vapor. That's a chemical change. Melting ice, well, it goes from a solid to a liquid form, but it's still water. So melting ice is also going to be a physical change. And finally, grinding cinnamon. You're taking a stick of cinnamon and you're turning it into small little, powder of cinnamon. That is as well a physical change. Okay, so now we've talked about matter. Now, one of the things that we really need to discuss in depth before we can kind of move on and talk about energy is we need to understand temperature. Now, we're going to talk about it in terms of that we've always used temperature, right? Temperature is a concept that you're familiar with from your normal life compared to, what we're learning in science class. And we're going to talk about the kind of microscopic basis for temperature in this class. So let's go ahead and start by defining temperature. Temperature is a measure of how hot or cold an object is compared to another object. You can measure the temperature using a thermometer. And in lab, we're going to be using units of degrees Celsius rather than degrees Fahrenheit, which you might be familiar with just from being here in the United States. Okay, so this is why we have to go ahead and define this real quick, is the difference between the Fahrenheit, Celsius, and finally the Kelvin scales. These are the three different scales of temperatures that you might be familiar with. Fahrenheit, pretty much only used in the United States. And then Celsius, which is used in much of the rest of the world for everyday temperatures. And then finally, we have Kelvin. That's what's useful in science in particular. Okay, so let's go ahead and take a look here at Fahrenheit, Celsius, and Kelvin, how they stack. So the reference points that are going to be listed here are the boiling point of water, the freezing point of water, and then normal body temperature. So for Fahrenheit, the boiling point of water is 212 degrees Fahrenheit. Normal body temperature is 98.6 degrees Fahrenheit, and the freezing point of water is 32 degrees Fahrenheit. So, so this is kind of the scale here, and the idea is that there's 180 degrees Fahrenheit from the freezing point of water to the boiling point. Now, if you're not familiar with Fahrenheit, you're not going to need to know it for this class. Don't really worry about that. Just be able to apply the conversion equation that I'm going to show you on the next slide. So Celsius, again, this is the one that we're going to use in lab a lot more. The boiling point of water is defined as 100 degrees Celsius. The freezing point of water is defined as 0 degrees Celsius. Then our normal body temperature in this scale turns out to be 37 degrees Celsius. So it's, it kind of gives you the same idea. Now Kelvin, so this is, Celsius is useful every day because these are temperatures that we're familiar with. Kelvin, on the other hand, is really only useful in the science lab because, as you can see here, the freezing point of water starts at 273 Kelvin. The boiling point ends up at 373 Kelvin. It's like if we were trying to use those every day, it would be kind of difficult to adjust to what those temperatures actually mean. And the normal body temperature ends up being 310 Kelvin as well. Okay, so real quick, we're going to talk about how you can convert from Fahrenheit to Celsius. I will not be asking you to convert from Celsius to Fahrenheit, just from Fahrenheit to Celsius, because that's going to be what's important in our classroom. So note here that we talked about there's 100 degrees Celsius between the freezing and boiling points of water, compared to 180 degrees of Fahrenheit between the freezing and boiling points of water. So if you do the math, you find out that for every 1 degree Celsius, there's 1.8 degrees Fahrenheit. And that's just like purely off the scale. You're not talking about the numbers themselves. You're just saying for every degree Celsius, there is 1.8 degrees Fahrenheit. Now, the problem is you actually need to be able to convert from Fahrenheit to Celsius. And, oh, don't we have it here? Okay, sorry, I think it's on the next slide here. In order to convert from Fahrenheit to Celsius, you also need to account for the difference in the fact that 0 degrees Celsius is 32 Fahrenheit. So we'll talk about that in a minute here. Okay, so we're going to do a quick learning check. You can pause the video now if you want to. If not, we're just going to go through it here real quick. A, what is the temperature at which water freezes? Is it 0 Fahrenheit, 0 Celsius, or 0 Kelvin? The answer is 0 degrees Celsius. What is the temperature at which water boils? Is it 100 Fahrenheit, 32 Fahrenheit, or 373 Kelvin? Well, 373 Kelvin is 100 Celsius, which is the temperature at which water boils. So it's 3 in this case. And then how many Celsius units are between the boiling and the freezing points of water? That's between 0 Celsius to 100 degrees Celsius. So that is 100, number 1. Okay, here we go. This is actually what I wanted to get to here. For the ability to convert from Fahrenheit to Celsius. So we know that there's 1.8 Fahrenheit degrees for every 1 Celsius degree. So that gives us, if we take the temperature Celsius the temperature in Celsius, multiply it by 1.8, that's going to change our temperature. But we also have to adjust the 0 point, the freezing point. So that means we take plus 32 to account for the 32 degrees difference between the freezing point of water in Fahrenheit versus the freezing point of water in Celsius. So here's our final equation here. The temperature in Fahrenheit equals 1.8 times the temperature in Celsius plus 32. Now, the thing is, I'm not going to really ask you to do that. I am only going to be asking you to convert from Fahrenheit to Celsius because Celsius is going to be what we're going to use in this class. I don't know if in the medical field you're going to use Fahrenheit or Celsius more. You know, like when I take my son in to get his temperature measured or whatever, the thermometer is in Celsius. So you probably want to be more familiar with Celsius from here on. But this is the actual equation you want to use there. You take the temperature in Fahrenheit, subtract 32 from it. That normalizes the zeros on both scales. Divide it by 1.8. That gives you your temperature in Celsius. So that's the equation that you're going to want to be able to use. So let's go ahead and look at a typical temperature problem. So the typical temperature in a room is 21 degrees Celsius. What is that temperature in degrees Fahrenheit? Well, we know that our Fahrenheit temperature is going to equal 1.8 times the temperature in Celsius plus 32. So all we have to do is substitute our temperature that we're given here in the Celsius term in for the equation here for T sub C. So we take 1.8 times 21, add 32. Keep in mind here that the 1.8 is exact and the 32 is exact. These are both exact numbers. So the only number that has any significant figure applications is the measurement of temperature, which is 21. It ends up being 38 plus 32. We end up with 70 degrees Fahrenheit. And because we know this one to the ones place, right? So this is going to give us to the ones place here. That means our answer should be known to the ones place as well. Ooh. There we go. Okay, now we mentioned already the Kelvin temperature scale. The Kelvin temperature scale is fortunately very easy to convert to and from when you're just going to Celsius. So now why do we have the Kelvin temperature scale? Well, the Kelvin temperature scale is actually not a degrees scale at all because 0 Kelvin is the coldest temperature that's possible in the universe. This is what we call absolute zero. Now, the reason that it's the coldest temperature possible, I'll just explain this very briefly. We talked about the motion of particles relative to one another already. And as substances get hotter, their particles are moving relatively fast. As they get colder, they move slower and slower and slower. Now, eventually, they would have to move slow enough to stop, completely stop any motion at all. And that is what we call absolute zero. And that is the coldest temperatures that's possible. So for science terms, Kelvin's very useful because it's going to directly relate to how fast the particles are actually moving. And that's kind of what we want to use in science terms. So a few more important differences for the Kelvin scale compared to Celsius and Fahrenheit. Note that when we talk about kelvins, we actually don't use the degree unit, right? So the lowest possible on the Celsius scale is the absolute zero is negative 273 degrees Celsius. That is just 0 Kelvin. There's no degrees there because there's no, it's not a degree scale, basically. We have an absolute zero, which is 0 Kelvin. And so it's just like saying, 1.23 grams. Well, 0 grams is 0. Same thing with temperature in terms of Kelvin. So don't use the degree symbol with the Kelvin symbol. Also, negative Kelvin temperatures are impossible. So no negative Kelvin temperatures will exist. The convenience here is that the units of Celsius are the same as the units of Kelvin. So 1 Kelvin equals 1 Celsius degree. And to convert from Celsius to Kelvin is very simple. You just take the Celsius temperature and add 273 and 273.15 if we need to do that in lab, just so you know. So it's a very easy conversion. And so again, this is why Celsius is what we're going to use in lab. And then Kelvin is what we'll use for some calculations in the future. Okay, so let's go ahead and do sample exercise 4. We have two different temperature conversions. Let's go ahead and give it a shot. So what is normal body temperature of 37 degrees Celsius in kelvins? Go ahead, convert Celsius to Kelvin, give it a shot, and we'll go over the answer here when we come back. So go ahead, pause. We're back. Let's go ahead and take a look here. Remember, the Kelvin temperature is the Celsius temperature plus 273. So what you're going to do is take your 37 degrees Celsius and plug it in down here. So we know that it's 37 plus 273. So keep in mind now, this should be like 0.15 here, just so you know. And that would be exact. It's exactly 273.15. But of course, the important part for significant figures is the measurement of the Celsius degree. So we know this 37 degrees Celsius to the ones digit. So that means we're going to know our answer to the ones digit as well. So do the calculation. We end up with 310 Kelvin. And again, we know it to the ones digit. And that is the correct answer. Okay, 4B. Okay, so on a cold winter day, the temperature is negative 15 degrees Fahrenheit. What is that temperature in degrees Celsius? Go ahead, pause the video, work it out using the formula that we used up top that I showed you before, and then we will convert this temperature into Celsius when we come back. So go ahead, pause the video. We're back. So remember, the formula here to convert Celsius or Fahrenheit to Celsius is you take the temperature in Fahrenheit, subtract 32, divide by 1.8. Keeping in mind, 32 and 1.8 are exact numbers. So these, are not going to affect your significant figures calculations. So for the Fahrenheit temperature in this case is negative 15 degrees Fahrenheit. We know that to the ones digit. That means that we're going to know the answer to this problem to the ones digit as well. So go ahead and take negative 15 minus 32. That's going to end up being negative 47 divided by 1.8. So hold on, 47 negative divided by 1.8 equals. So it's two significant figures up top, and this is an exact number. So that means our answer is going to have two significant figures. So I end up with negative 26 degrees Celsius. There you go. Just so you know, when you see this on your calculator, you probably got negative 26.11111. But remember, we can only have two significant figures because we only have two significant figures up top. So that gives us two significant figures here. Okay, so the answer is negative 26 degrees Celsius. Okay, so yeah, this is just a table to compare like some temperatures of interest, basically. Starting all the way at the bottom, absolute zero, which is negative 459 Fahrenheit, negative 273 Celsius, and 0 Kelvin, and building all the way up to the temperature of the sun. Now, most of these, absolute zero doesn't really matter to us. The temperature of the sun doesn't really matter to us. It's mostly we're dealing in the scale here from, water freezing to water boiling. Okay, so we're going to talk very briefly about a health temperature variation that you may see in your future career, which is hyperthermia or hypothermia. So hyperthermia, hyper means like more than, thermia of course is temperature. So this is like a greater temperature than normal. And any body temperature that's above 41 degrees Celsius is called hyperthermia. It can lead to convulsions and potentially permanent brain damage. Heat stroke will occur above 41.1 degrees Celsius. And if you have a patient with heat stroke, you may immerse them in an ice water bath to like get them down to temperature just more quickly. The key thing is, the higher the temperature, the more molecules are moving, the faster they're moving, and that can cause problem for like your neurons, for example, in your brain. Now, the other scale is hypothermia. Hypothermia is when your body temperature is going to drop as low as 28.5 degrees Celsius. In this case, what you need to do is you need to provide oxygen and increase blood volume by using glucose and saline fluids, and also injecting warm fluids up to normal body temperature, that is 37.0 degrees Celsius, into the peritoneal cavity to help restore that internal temperature. So both of these situations can occur. You know, living in San Diego, maybe hyperthermia is a little more plausible than hypothermia, but both can happen. And who knows where you're going to be? Who knows? Okay, so here we go. A person with hypothermia has a body temperature of 34.8 degrees Celsius. What is that temperature in degrees Fahrenheit? Well, I already told you I'm not going to ask you to convert Celsius to Fahrenheit, only Fahrenheit to Celsius. But let's go ahead and step through this. Let's walk through this example just to be, just to make sure that we understand it. So if you have a temperature of 34.8 degrees Celsius, what you're going to do is take that temperature in Celsius and plug it into the temperature equation, which is 1.8 times the temperature in Celsius plus 32. So all you have to do, plug in your 34.8. You know that this measurement, to the 10th place, this is an exact number, this 1.8 conversion, as well as this 32 here is exact. So we get 62.6 because there's 3 significant figures here multiplied by an exact number, 3 significant figures here. This one again is exact. So think of it like this way, it's basically 32.00000. So to get our answer here, if we know this measurement to the 10th digit, then we're going to know our answer to the 10th digit as well. And the correct answer would be 94.6 degrees Fahrenheit. Okay, well, that does it for this lecture, but we're not done with chapter 3 just yet. Come back for the next lecture and we'll wrap it up talking a lot about energy and how energy interacts with matter. So I'll see you soon.